This is another question that often comes up when people are starting to explore energy efficiency improvements. So Kevin, is energy efficiency the same as energy consumption?
Well, the short answer is no. Energy consumption is how much you use. You can see here a typical scenario for a big energy user. The left-hand bar shows the amount of energy used, categorised by the three energy sources they use: gas, electricity and diesel. It shows energy consumption in gigajoules. All energy can be converted into joules, or if you're a big user, gigajoules, as they've done here, as the common measure of energy. If we're doing this graph just for electricity, we'd probably use kilowatt hours or megawatt hours if you're a big user, which are related but different unit and is specific for electricity. This graph also shows in the middle bar there the cost of buying these amounts of energy. And so by comparing the left-hand bar with the middle bar, we can get an estimate of the relative cost effectiveness of each source of energy. It also shows the equivalent tonnes of CO2 being produced. All of these forms of energy burn a fuel to produce CO2. And so they all do produce CO2, and this then can be used to compare the impact of the different forms of energy. But we're not covering that side of it today. So this gives us energy consumption, but doesn't tell us how much product or service was produced for that energy consumption. Energy efficiency is far more useful for that. So consumption tells us how much. We measure it in joules or megajoules or gigajoules or kilowatt hours if it's electricity. But how much are we going to be using to produce a desired change compared to how much, in theory, do we need to use? This is efficiency. Mathematically, this is a ratio of the energy that's required over the energy which is actually used. And so we can calculate out our energy efficiency. The easiest way to look at this is to take a simple example. So we're looking at my office kettle. If we're going to calculate the efficiency of my office kettle, we need to collect a bit of data before we start doing our sums. So we pick up the kettle and we have a look at it. The rating plate tells me it has 2200 watts. Okay. I put 1 litre of water in it. Fortuitously, that equals 1 kilogram. We'll come back to it and we'll use that again later on today. We need to know what temperature the water is going in, 20 degrees C. We boil our 1 litre of water and we time how long it takes, and we find it takes 2 minutes and 55 seconds for it to come to the boil when you can hear it bubbling, and another 7 seconds before the kettle actually turns off. Now that's interesting because it's already boiling, so this 7 seconds is a waste we've identified straight off. And then to do the maths, we actually need a thing called specific heat capacity of water. You can look that up in a textbook or just Google, it's easier. And that turns out to be 4.210 kilojoules per kilogram Kelvin. This is defined as the amount of energy required to raise 1 kilo of water by 1 degree. So we've now got all our data. So let's get on and do some sums. So how much energy would you use? Well, energy used is watts times seconds. A watt is a joule per second, so if we multiply it by the seconds, we end up with joules, which is what we want. So let's start doing the sum. We said we had 2200 watts, 182 seconds. We've converted the 3 minutes and 2 seconds into seconds. So we multiply 182 by 2200, and we get 400,400 joules, which of course is 400.4 kilojoules. So that's how much my kettle actually uses. But how much do I actually need? This is a straight physics question. While the amount used is a property of the kettle, the amount needed to actually boil the water is a property of the water. I might be able to change the efficiency of my kettle. I can't change the properties of water. Remember, a litre of water just happens to weigh a kilogram. That's very convenient. Remember, the heat capacity of water was 4.210. So we start doing a few sums. We multiply 1 kilo by 4.21, and then by the number of degrees that we increase the temperature. So It starts off at 20, it ends up at 100, which is the boiling point of water, so we increase it by 80 degrees, multiply all those together, and I get 336.8 kilojoules. So, energy used, 400 kilojoules, energy needed, 337 kilojoules. Take one from t'other, and I find I've got 63.6 kilojoules that's just gone somewhere. Has not gone into boiling the water. So where's it gone? Well, it's obviously just waste. Some of it's just wasted into the air. Some of it's wasted up eating the kettle itself. I guess I've got to put up with that. And some of it is also wasted because the kettle kept boiling for 7 seconds after it had actually reached boiling point. So if I combine all of this together, I can work out the efficiency of my kettle. So, something missing on the screen. So if I take my 337 kilojoules, just rounding off here, divide it by 400 kilojoules, multiply by 100, I find my kettle is 84% efficient. So, efficiency is a much more useful concept. I'm going to use 440 kilojoules every time I boil, 400 kilojoules every time I boil a litre of water. So if I have 6 cups of coffee in a day, that's 2,400 kilojoules I'm going to be using. But if I use the efficiency, I can use this, I can now compare two different kettles. Which one's going to be more efficient? I can measure the amount I use. I can measure the effect of insulating the kettle. I can measure various other effects. So efficiency remains the same regardless of how many cups of coffee I have, whereas consumption is just the blunt, bald figure. So it's sometimes possible to reduce our costs by improving our efficiency. Or for sometimes we can reduce our costs without even improving our efficiency. So for example, you might do a negotiation with your power provider just to purchase power at a lower price. And you might do this because you can buy it at off-peak power. And if you're doing this, maybe a smart meter will help you. Maybe you've been able to reduce your peak demand, and we'll talk about that later today. So this will reduce your power bill, your cost of power, without reducing the amount of electricity you actually use or improving your energy efficiency.
Okay, and we've got an excerpt now from one of the energy efficiency videos, and it is on this topic. And the videos are available from YouTube and from the website, and we'll give you those URLs again later.
Our energy is measured in 3 different zones. We've got peak time, off-peak time and shoulder time. So what we started doing there is to look in what tariff zone are we using our equipment. So if we could run certain machines in the off-peak times, we'd do that. So they didn't necessarily save us energy, it saved us a lot of money.
Staggering the start times for machines, which sounds like it's not going to do anything. If you're going to stagger the start times, you're just going to start later and finish later. But if all the machines start at the same time, their peak demand increases, and that can greatly increase our power charges. So staggering those starts keeps that peak demand low.
Some of our businesses that we interviewed talked about improving their power factor as one of their approaches to improving energy efficiency. Kevin, what is power factor and why is it important?
Thanks, Celeste. Power factor is a phenomenon associated with use of AC power. We all use alternating power. It relates to the efficiency with which the electricity delivers power. And when you're using alternating power, as shown on the slide, the voltage and the current both oscillate up and down. Ideally, they do so at the same time, as shown here, and this is said to be in phase. However, as you run it through your equipment, the voltage and the current get out of phase, as shown in this slide. And what this means is that they are not delivering the same sort of power as the power that you are buying. So a power factor of 1, as shown in the previous slide, means you're using 100% of the power. You're getting great efficiency. A power factor of 0.75 means you're only getting 75% of the power you're paying for, or you're only using 75% of the power you're paying for. So all electrical equipment using this out-of-phase power supply will only be 75% efficient. We can get power factor correction equipment which moves these things back closer to being in phase, as shown here. The closer we can get back to a power factor of 1, the better. This is something which is beyond the scope of this webinar, but your power provider will have some options that you should discuss with them. So energy efficiency is not the same as energy consumption, but they are related terms. Typically, we're trying to improve our energy efficiency to reduce our costs. And energy efficiency allows us to do this by allowing us to use less energy for the same output. We may also want to do this because we want to make an ecological contribution, make the business more ecologically sustainable, or to be more green, or to make contribute less greenhouse gas. And so this is good for the environment and may also give the organisation some sort of marketing advantage. For a business with growing demand, improving energy efficiency might also have more tangible business benefits. We're all wired up for a specific maximum demand. We're normally not aware of this until we start bumping up into the limit. And we go to increase our energy use and we find that we can't until our supply is augmented. This can be quite an expensive process. We might have to upgrade our fuse box, we might have to upgrade the wires supplying the power to the premises. If we're unfortunate enough to be in an area where everybody's bumping up their rated supply limit, maybe the whole substation needs to be upgraded. This is an expensive process and can cost you hundreds of thousands of dollars. One of the businesses we spoke to were facing a $250,000 upgrade to their supply. But they found with a $17,000 investment in energy efficiency, not only were they able to stay within their limits, not spend the $250,000, but also they saved $12,000 a year. So this was a real win-win situation.